Okay, let's begin for today. I think I need to make a new one. Okay, here we are. So let me just do a few announcements first, and then we'll begin. Infinite recursion, yeah. Well, we're going to do something like that. So basically, just a reminder, Project 1 is due this Friday, at which point Homework 6 will come out sometime Friday, maybe mid-afternoon or something, hopefully. Yep, and then a week after that, we're going to have Project 2. And I think during Project 2, unfortunately, we're also going to have the second midterm. So that's how the semester is currently going. Okay. Let's see. What else should I say? Let's get the page border. Okay. So the thing that I want to talk about, yeah, unfortunately, it's during Project 2, at least the first week. So it's going to be a bit difficult, but unfortunately, it's just the way that the timing works out this semester. Yep. Okay. Will it be the same format? Yes, same format. It'll have some MCQ questions, plus probably 5 coding questions. And so that's about the same. Okay. What else do I want to say? I think that's it for announcements. I don't really have anything more. At least not right now. So let's begin. Let's talk about pathfinding again. So recall last time we were talking about pathfinding. Last time we were discussing pathfinding. And the issue with pathfinding is that let's actually just draw a bunch of squares. Let's see, can I draw maybe a little smaller? There we go. This will be a square. And now let me make a grid out of these squares. So let me make a grid. And then let me make okay, here's a grid. Now, say that this is our start. I don't know, let's say that this is our starting square, so let's color that dark blue, and let's color the ending yellowish. I guess maybe it's something a little lighter. There, maybe that's fine. Or let's just pick whatever this thing thinks is yellow. Okay, so how do we find it? And let's X out a certain number of spaces. So anything that's, we want to make this a little brighter. So this is the start, this is the end, and anything that's blacked out is, say, forbidden, or just you can't get there. So let's just pick some random squares and do that. And then I'm going to show you kind of the idea of searching, right? And I know that the program does it, when I've shown it to you, but let's actually do it slower and kind of more methodically. So basically, when you start at this square, what you're going to do, right? So what you're going to do, let's see, this is 1, 1, right? Or yeah, so this square basically is 1, 1. If we start numbering from, say, 0, 0 up top. So if we're at position 1, 1, then what we have to do is we have to call search for path on position, say, If we go up by 1, it'll be 0, 1. We also have to call for it on position 1, 2, right? Well, I guess I should be careful which thing is x and which thing is y. So let's call this axis the y-axis, and let's call this axis the x-axis, and let us have the points are going to be in x, y. So basically, let's be more careful about this now. So let's say, so if this is x, y, then actually we would want to call it on 1, 0, because that's x, y, and then here we'll call it on, say, what's the next one up? So it would be, say, 1, 2. Actually, this is correct, right? X equals 1, y equals 2. And then we have to call it on the two different x positions. So say, keep y1 as the same, and then call it on 0, and call it on 2, like this. So this is all the stuff that we need. If you're trying to find the fastest path, wouldn't you have to know where the end is? It depends. I think the whole thing is that if you're searching for a path, you don't know where the end is, right? So there are ways to find the fastest. And I guess I should also be more careful too. When we say find the fastest path, do we mean find the shortest path from this position to this position, or do we mean find a path in the shortest time? And those are two different questions, actually. Normally it's a trade-off between the two questions. Is if you try to find the absolute shortest path, it takes you longer. It takes you longer, and so if you knew where the end path was, then you could definitely do some optimization. But then there would always be bad cases. So if you built yourself like a spiral shape, then just trying to head for the destination wouldn't always work. Anyway, okay, so okay, let us continue. So here we have to call these functions. Now, once we enter this function here, the search for path 1, 0, what are we going to see? What we're going to see is that now we are, I don't know, I'll pick a different color for this. This. So this is where we currently are. Let's make it green. So green is where we currently are, right? Current equals green. There we go. And so here's the thing. If we're up here, then the next thing we're going to do is we're going to call a bunch of different functions. And so let me tell you what those functions are. So first, it's going to call search for path. So it's going to check here, and it's going to say we can't go up, so we can't call search for path 1, -1. So it would try to call it with 1, -1, but that's out of range, so we're not going to do that. The other thing that it would try to do is it would try to call it with search path, say, let's see, y is equal to 0, x is equal to 2, right? And that would be this position. Y is equal to 0, x is equal to 2, 0, 1, 2. And you would notice here that this is blacked out, so we're not going to call it there, right? And so the other position that we're going to call is search for path 1, 1 again. So let's assume that we search for path along 1, 0 and say we don't find anything, or it's forbidden or whatever. Then here's the problem, right? Search for path 1, 1 was the initial condition. It's where we started, right? And so if we do this without some kind of solution for this problem, then we're going to end up with an infinite recursion, because what's going to happen is, let's just pretend that search for path 1, 0 doesn't end up working. And maybe in order to force it not to work, we can black this out too. So I guess then also technically this would be blacked out, yeah. So, but the point is here, if this is blacked out, then it tries to go this way. It can't go this way, right? So it's going to pop back up the recursion, and with that, what it's going to do then is it's going to try to search for path 1, 1. When it tries to search for path 1, 1, then it's going to put it right back into the search for path 1, 0, which is up here, right? X equals 1. Let me just draw it in. This is 1, 0. This is, what is this? 2, 1. This is 0, 0, right? Etc. So the point is that we're going to end up with this infinite recursion, And so we have to find a way not to do that, right? And there's a number of different ways that you can do it, but I think like the fundamental idea behind most of the ways is to establish either some kind of basically some kind of way to mark where you've been, okay? So the solution here, now that you've had a few seconds to like think about the problem, and the problem is that if we took out some of the code from what we were doing last time, we'd end up seeing that we would go from here up to here, and then this path would search over here. Okay, didn't find the yellow square, so now we're just going to come back here, and the problem is that this square, the next command that this square executes is search for path on the blue square, which then calls search for path on green again. And it just goes, yeah, exactly. We have to find a way to exclude paths already checked. And notice here, we can actually do something even more aggressive. We can exclude spaces already checked. And the reason why we can exclude spaces that have already been checked, and if you think about it this way, if a space has gone through its search, then no path coming out of that space will work, right? And if that space returns a path, of course, if that space returns a good path, then we know that we can step there to get to yellow, right? And if we can do that, then we know that we have an answer. So either we're going to get like a return none or a return empty list or something, and if we get that, then the thing is we know that then we know none of the paths coming out of that space is going to work. So we don't have to necessarily mark all the paths, because see, the thing about paths is that they're very complicated, because you could have a path that, for instance, if you're not careful, you could have a path that says, let's go here, then down, 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 over, up, right? And then it's a loop, and you could keep doing that, and your path could do that 14 times before it finally goes to the solution. Now, our algorithm isn't going to do that, but it could happen, right? So one of the ways to do this is to mark spaces as visited, right? So you can either call it like marking spaces or setting them to visited or something like that. So let me show you an example. Let's actually recode all of the stuff that we did, except let's do it in text format. So let's do Pathfinding text version, right? Okay. So I'm going to have a generate grid function, and let's say x and y is going to be the grid that we're going to generate. So y is the vertical axis and x is the horizontal. So so we actually have to flip it. So okay, and what I'm going to do is I'm going to import random, and you'll excuse me for doing that, I hope. Random.choice, and the only choices we're going to have are what are the choices we're going to have? We're going to have true and false, okay? And what those are going to stand for is, accessible or forbidden, right? And so random.choice is just going to pick one of the things out of this list with a probability 50-50. I think we can actually have probabilities other than 50-50. I think we can make like maybe true. We want that to be something like 0.8, and maybe this is like 0.2. If I'm not wrong, you can actually do that in the random.choice function. Let me check out random.choice and just double check that I can put the probabilities in. No, not in choice. There's another function that's like choice that you can do it with weights, right? Yes, okay. It's not random.choice, it's random.choices. There we go. You could do that, yes. But I'm going to do this instead. Okay. So this is not really part of our recursion. This is just me generating a grid. So let's say here's the grid equals empty list for I in range y. row equals empty list for j in range x, row dot append this thing, grid dot append row, return grid. Done. So yeah, I just had to look up the random choices thing. I trust me, I know from experience when you let the weights get set to 50-50, you're gonna end up with a huge number of just impossible paths, right? Because if you notice, right, like the if half of the squares are forbidden, then it's almost certain that you're just not going to be able to find your way to the answer. And let's make a draw grid function. And so the grid. And so here what we're going to do is, I don't know if I'm going to use so many, let's see if I'm going to do anything forbidden. I guess, yes. I'm being very lazy here. So, nope, this is not right. This will not produce the correct answer. So, let's see. Let's do it the legal way anyway. Okay. I know it's not as cool, but I think that should be a little bit better. Okay, so now let's generate a grid, say of 5, 5, and then let's draw the grid just to test our code. And remember, you should always test your code, because otherwise you don't know if it works. See, it didn't work. Oh, I know. Let's say a space or x. Okay, and that'll tell us. Let's see if this works. Nope. Expected string instance list found. The grid I is a list, so we have to join it. I think I do have to do. The grid I is a list, right? That's what we wanted. Yes. Let's see. Expected string instance list found. Yes, but join takes a list, right? Oh, wait. Is the thing still... Okay, now I'm confused. Let me just print out what comes out of this thing. Oh, it's a list containing... Yeah, see, it's a list containing... that. So the simple way to fix that is just to do this. Okay, there we go. That's better. Now we can... So the grid equals that. Now we can draw the grid. And so hopefully I have kind of made the... good. Okay. Let us put a period if it's allowed and an X if it's not, so we can see. Okay, there we go. Cool. All right, so that's good. All right. So now that we've done that, now we can make the pathfinding algorithm, right? None of this was anything interesting. This was all just some stupid stuff. So pathfind, right? And we'll have, say, a starting location, or maybe we'll have current, which will be a starting location, and then we'll have some visited list, and then we'll have current, and then maybe destination. Those are the things we need, right? So let's see what happens, right? Okay. And then I guess what we'll have to do is do some testing in just a second. So, okay, wherever we are, we're going to say if, and so remember that current is going to be a tuple, right? So let's document this code a little bit. So current is going to be a tuple, xy. Destination is going to be xdest, ydest. And visited is going to be, let's say it's a dictionary of visited tuples. Okay? So, and then it's going to return, say, empty list if no path, else a list which has a bunch of tuples, right? x0, y0, down to xn, yn, which is a path from the start to the destination. So we have to think about our recursion, right? When does all this recursion bit stop? And this is kind of the easiest thing to think about. If the current is equal to visited, destination. If current is equal to destination, then we're done, right? So then all we have to do is return, let's say that we return, and for no reason, I'm going to return a list containing the destination, okay? You might be like, why are you putting in a list? Why not just return the destination? Blah, 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 blah. Don't ask. I'll tell you in a minute. Okay, so if the current is equal to the destination, we're done. So we would call this like the base case of our recursion. And then we have basically 4 cases, okay? And so the 4 cases are these, right? So in the 4 cases, let's go through the cases. So wherever we are, let's draw a big square. And let's not make it black so that we can put some text in it. So wherever we are, there's 4 squares around us, right? So let's call our position xy. And then let's compute the positions around us, so that we can know where we are. So if we're at xy, we have to search at xy minus 1, right? Because that's 1 up. We also have to search at xy plus 1. We also have to search at x plus 1y. And we also have to search at x minus 1y, right? Those are these 4 different positions here, right? So x minus 1y, we go back 1. X plus 1y, we go forward 1. We go up, so this, and then we go down, right? So xy minus 1 and xy plus 1. So those are the 4 things that we have to search, okay? So I'll save this. Well, no, I'll save this now. You know why I'm going to save this now? Because Inkscape can crash. We'll do Pathfinding 201. Okay, so let's go back here and let's code that up. So how do we do it? We have to, actually, we got to do xy minus 1. We got to do xy plus 1. Maybe x plus 1y, and then x minus 1y. Right, so these are the 4 places to look, right? And so what we're going to do is we're going to say if 0 is less than or equal to, say, y minus 1, right? And why do we have to do this? What we have to do this is because, first let's get x and y. So x is equal to current 1, y is equal to current 0. There we go. So if 0 is less than or equal to y minus 1, and the reason why we have to do this is so that we don't accidentally move off the board, then what we can do is we can search, right? Search, or what is it? Find path. What did I call this function? Pathfind. Okay. Then we want to pathfind to the new point, which is x, y minus 1, right? And destination visited. And you might be like, well, I haven't filled in all the other things. So, and then if x plus 1 is what? Less than or equal to, and we don't really care if it's, right, it's going to be bigger than or equal to 0, right? This end is okay. It's never going to be under the bound. It's only going to be over. So if this is less than or equal to the length of the grid at y, that, and of course we're going to assume it's a square grid, but this is actually a little bit more general. And the reason why we have to do this is because actually the grid works this way. The grid actually takes coordinates as y, x. So if x plus 1 is less than or equal to the grid y, then we can, oh wait, no, I'm wrong. What am I doing? Oh no, I'm right. I just haven't changed this yet. So x plus 1 and y. Cool. Now let's copy paste these two things and let's do it again. So here we're going to do x, y plus 1. So now we don't care if it's bigger than 0, we care if it's less than the length, I'm sorry, this should not be equal to, less than the length of the grid. Then we can do this on y plus 1. And then here we can do this on my y minus 1 if x minus 1 is bigger than or equal to 0. And we don't, technically we would have to check this, but we don't actually care because subtracting 1 will never push us above the length. So these are the 4 things. So this is basically the code, right? But here's the problem with this code. So let's say that we wanted to try to find, say from 0, 0, I don't even know if it's forbidden or not, but who cares? It's 0, 0 to 5, 5, and let's say we just put in an empty dictionary. So what we're going to do is we're going to try to go from 0, 0 to 5, 5. Now let's see what kind of thing it gives us. Blah. So immediately we get an infinite recursion, right? Maximum recursion depth exceeded. And the reason that we're getting this infinite recursion, so Python doesn't actually let us do infinite recursion. When I say infinite recursion, what I mean is that we get to the recursion depth. And what that means is that basically Python is saying, you've tried to do the same function so many times that I'm not going to allow you to continue, because I think you're stuck in an infinite recursion. It thinks you're in an infinite recursion and it stops you. So, but that's also not good because also our code crashes. So how do we prevent that? Well, what we do is we say, once we're at a current position, right? Once we're here, we can set visited of, and then here's the cool thing about tuples, because they're immutable. You can actually use this, right? And then you can say, yeah, it's essentially infinite. It's just Python is slightly preventing you from doing this. So what you do now is you say and not, and maybe, yeah, and x, y, or x, y minus 1, not in visited. Okay? So what that's going to do, and watch how this is going to fix everything. So what we're going to, I think it's going to fix everything. Maybe it'll fix everything. We just have to make sure that this should be y plus 1, and this should be x minus 1. We see here, this is where I add it to the visited, right? So I'm making visited a dictionary. So visited is a dictionary. And here is where, well, I already did that last class, right? So, but here I'm just recoding just the pathfinding parts so that you can look at the, I mean, if you want to do the pathfinding visual, you can always run the pathfinding visual code, which is this, right? And you can click the start, you can click the end, and it will search, right? This is what our code is about to do. It's just going to do it in a slightly less visual way. The reason why I don't the reason why you have this code, but the other reason why I'm recoding everything is just to show you how the code works, rather than, if you looked at this code, the Pathfinding visual code, you'll notice that all the stuff that I'm about to type is in there already, except there's also this extra garbage, which makes the graphical, the GUI interface, right? And you don't right now have to care about like this part or this part or any of this code, right? Well, I'll show you. So how's it getting added to visited? This is how it is, right here. Here's where we add the tuple into the visited dictionary. And so basically, now the dictionary remembers the tuples where we've been, and we won't go there again. And the reason why we won't go there again is because I've added all of this and not in visited, and not in visited, and not in visited, and not in visited, right? If it were in visited, we could potentially debug, but we're not done yet. So first we have to finish, right? We're not done yet. I mean, well, let's see what happens if we run this code. Let's see. Also, we need the grid, right? Oh. Okay, well that was dumb. I think the grid was just functioning as a global variable. And you know how I feel about global variables. They're not great. So here we go. Let's try this again. Let's try pathfinding text again. Maximum recursion depth exceeded. Okay. So, interesting. Why did this... So, okay. There was a path, but instead of finding the path, you know what, let's actually print out where we are every time. So let's print out, we are at, well, let's just do it this way. Something like that. And then I think we're still going to get loops, and I'm not sure why we're getting loops, but let's see. We are getting... unfortunately, if you think about it, if you display a row, and that is your first array, then the first index is actually the y-coordinate. So for instance, interesting. Look at this. 2003, 2003, 2003. Now you shouldn't even be able to get to there from there. That should not even be possible, right? Why is this happening? It's a good question, I guess. So, why is it happening? Unless, of course, I'm doing some kind of flipping or something. But I'm using this as y. Interesting. Why is this? So the good news is that I've never yet been able to do this perfectly on the first try. And clearly there's some problem here with flipping back and forth between 20 and 03. Right? That should not be possible, because whatever you get out of this, it should be like 1-1 or 3-1 or 2-1 or something like that, right? It should not be possible to get 0-3 out of that, because if you could do that, then you would have to subtract 3, or you'd have to add 3 to one coordinate and subtract 2 from the other coordinate, which we are never actually doing. So there must be, I must be flipping something somewhere. And of course you might suspect that I'm flipping it here, which is always possible, but I'm hoping I'm not. Yeah. Interesting. Interesting. And of course it's gonna, I'm sure it's gonna do the same thing if I run it again. Yeah, 2, 0, and 0, 3 again. So something's getting flipped somehow. Here's x, y plus 1. I'm just not seeing something. There's something I'm not seeing. It's either obvious or it's not obvious, right? Did I do a copy-paste error? What did I do? What did I do wrong? There has to be. So it depends what we're subtracting from. So if we're subtracting from y, we should be going, so y should be going technically up, and adding should be going down. Right, so technically this is down, this is, what is this, right, this is up, and this is left. Now, we're not done anyway, so I'm just a little perplexed as to how we're getting this. Because we shouldn't be getting it, right? We shouldn't be. We should be getting something slightly better. I am extraordinarily confused by my own code. It's not even that complicated. Yeah, this is, I mean, if this is the code that I think it is, then this is impossible, right? Because we're only adding 1 or subtracting 1 from an individual coordinate, so it's not possible to get this. Why don't we try to do it this way and just see what happens? And I mean, it's not great to do it this way, and I think if we fix that, then we should be okay. Yeah, let's just do it this way and see if this fixes it. Ha! It did. Look at that. So apparently me flipping things actually did screw things up. I'm not 100% sure why. It shouldn't have done, but it did. So, okay. Oh, I think it's because I would have needed to put yx as these tuples if I'm going to do it this way. Ah, that's why. Okay, anyway, so I think I got it. Okay, cool. So now that it's actually terminating, now we actually want it to return the path. So basically what's going to happen is if, let's just call this possible path is equal to this, and let's copy paste this all 4 times. There we go. And then what we're going to do is we're going to say if possible path, right? Meaning if it returns something that's not just an empty list, then what we're going to do is we are going to return the possible path. And maybe I'll do it this way: possible path plus xy, like this. And the only thing to realize is that this is going to be a possible path as a list. So I'm just going to do this. And at the very end, if none of these work, right, we're going to return empty, which means none of them returned, we didn't find a path. So, okay, let's see what happens. And so let's print out find path and see what goes on. Okay, so let's look at this thing. So we're starting at 0, 0, and we're trying to get here. It doesn't even know what forbidden is yet, so it should actually be able to work. Why doesn't it find it? It did find it. Interesting. Interesting. Oh, because 5, 5 is outside of the grid. It's actually 4, 4. Okay. There we go. Here's a path. So the path that it found is what? So it found the path that did... Okay, let's comment out the we are at so that we can actually see what's going on. So what did it do? It didn't understand that this was forbidden, and it just said, okay, the first thing we're going to do is we're going to go... I guess we're going to go over 1, over 1, over 1, over 1. Of course it's recursion, right? What do you think all this is? Right? Pathfind, 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 pathfind. Right? There's 4 recursive calls inside of this function. That's the whole point. Anyway, so the point is that yeah, you start at 0, 0, then you go 1, 0, 2, 0, 3, 0, 4, 0, and then you start heading down, I guess, 4, 1, 4, 2, 4, 3, 4, 4, right? So, so there we are. So the problem is that it actually hits a lot of the forbidden spaces, so now what we have to do, the last thing we have to do is make sure that the thing is not forbidden. So let's check to make sure that the square isn't forbidden before we go there. So is it forbidden? That's a good question, right? Well, okay, here's the easier way to do it. If the current, right, so, okay, actually we have the current position here, so if the grid, right, say, what are we doing? Are we doing xy now, or are we doing yx? I guess xy is equal to capital X, that's the forbidden, then we just return empty, okay? So this takes care of forbidden spaces, okay? So let's see what happens. So what did it try to do this time? So what it did this time was it said 0, 0, 0, 1, then it said 1, 1, 2, 1, 3, 1. Actually, why don't we have it, as it's returning, why don't we have it draw in the possible paths? So the grid at xy equals p, right? And so this is just a little bit of extra thing that we're going to do. This is not really part of the algorithm, but this is just so that we can see what happened. So let's run this again. Okay. Interesting. It didn't do it. Why didn't it do it? Help me. Why didn't it change the grid? Because grid should be mutable. Oh, we have to draw the grid again. All right, that's obviously why. Okay, let's try it again. There we go. So apparently it couldn't find, here's one where it actually couldn't find a path. Because if you notice here, it can't search through these x's, so it couldn't find a path. Let's try again. Okay, so here it did find a path. And the path was 0, 0, then it went to 0, 1. So this is actually yx in this case, 0, 1. Then it went to 1, 1, 2, 1. And then for some reason it decided to go back, which is fine, right? No problem. 2, 0, 3, 0, 4, 0. And then here it started to advance on the answer, 4, 1, 4, 2, 4, 3, and I guess it didn't fill in 4, 4. So that's how this function works, right? Is that it, and so let's call it again. Let's run it again. So we see here what it's doing is it's finding its way around this X here, so it's going down, 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 down by default. Then it tries to go over, up, over, down, and yeah, so if you notice, it goes from the destination to the start, and I did that intentionally because a lot of times people want to stick on the plus thing on the end. So the way to fix that is actually to do it this way. You just kind of stick on the current coordinate at the beginning, and so that will fix this problem. So let's fix that problem by doing this and run it again. Oh, it's it's locked. It can't get out of 0, 0. Let's try it again. Here it goes. So it starts here, goes here, goes here, goes here, goes here, 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 and then finally gets there where it doesn't overwrite. But now you see that because I've added it in the other order, I've put the whatever the current thing is on the front. And so when it gets back to the first node, it'll say, ah, here we are, 0, 0 is our first position, this is our second position, instead of having to start at the end. So yeah, you can just, instead of doing, right, so this is instead of, right, instead of this. Yep. So, yeah, this is I like to go through this example, and if you really want, I mean, I'll post this, you can run this thing and you can debug it, and then you can also run the visual version of this and debug it. So this is basically just re-implementing the entire thing. You can change the size of the grid, you can do a bunch of stuff, right? So we've re-implemented pathfinding. So pathfinding is kind of difficult, but once you kind of know how to do it, it gets kind of formulaic, right? And of course, you know, you have to not make the kind of bugs that I did, and you have to code it up right, but you know, I've never coded it up correctly the first try. I've always had a few issues like that where I've accidentally flipped X and Y or something like that. It's hard to think about, but I guess it's good in a way because the point is that you see that it's not trivial to code. There's always a little bit of difficulty when you are coding these things. Anyway, so I'm not saying that pathfinding will be Project 3, but I do an entire pathfinding lecture now in 201 just in case we ever decide to, because we have had pathfinding Project 3s. So I want you guys to have enough pathfinding so that when you get to the Project 3, if we do pathfinding, you have a ton of resources that you can basically use for pathfinding. Okay, so let's talk about some other recursions. So what is this? This is recursive palindrome test. Yeah, so Project 2 is going to be Battleship. So the way I've kind of regimented this course is that Project 1 is Mancala, Project 2, but Mancala, so Mancala is the name of our project, but really it's a 1D list project. That's how you should think of it, 1D list. And then Battleship is actually going to be a 2D list project. And then Project 3, which I haven't decided on yet, but I have a few ideas. There's a few things, right? And this is the Recursion project. So examples of this project have been like family tree stuff, pathfinding, etc. Yeah. But anyway, that's generally how I think of the projects for this course, is I think to myself, I don't just think like, I want to make some games. I think, hey, I want a 1D list project. And so Mancala is a 1D list project, at least in my version. You know, Battleship, I don't really care about Battleship the game, but I do care about 2D lists, so there you go. And then Recursion project, you know, traditionally Project 3 has always been Recursion. There's been debate about whether it's too hard or not, but we're not going to debate that right now. Let's just do more Recursion. So now what I want to do is it's a common problem. And let me put quotation marks around that, scare quotes around common, because I'm sure that you will have never thought about this problem, but once you see the problem, then you will have thought about it. So it's a little silly test. It's like a, what I mean by a common problem is that it's like a hiring, interview type question, So here it is. I want you to display for me all the strings of A's and B's, right? More A's and B's stuff, where there are always more A's than B's to start, in the front. And so let me give you some examples. So AAB is okay, because here if you count up the A's, you'd say 1A, 2A, B. So the count of A's is always bigger than the count of B's, or I guess technically equal to in the start. But this one doesn't work. So ABA. So if I say there's always more, strictly more, then this one doesn't work because you'll have 1A then 1B. And so since the number of A's matches the number of B's, this one is good, this one bad. Let's do another one. AAAB, AAB, AB, right? This works because there's always more A's than B's. AAB, AB, AB, AB. This one also works if you think about it, because there's two A's, and then there's one B, then there's another A. So now we're at 3 and 1. Now we're at 3 and 2. Now we're at 4 and 2, 4 and 3, 5 and 3, 5 and 4. So this is always working. There's always more A's than B's. If the letter B doesn't work, right, because there's always because there's no A's, nope. BA, nope. Nope. Right? All of these don't work. Okay? As if there's one more A than B, or even if there's just AA, BB, right? Nope. But AAA, BB. Yep, that works. Okay. So let's write a recursive function that does this. Okay? So let's do that. Def more A's than B's. And so let's call the first thing length. That's the total length. And then we have to maintain an I guess we can even just maintain a difference. Okay? Now technically you can maintain an A count or a B count or whatever, and then we'll have the current string. Alright? And you'll see what we need all this for in just a second. So if we're going to do more A's than B's, the first thing I'm going to do is I'm going to use some default arguments. So if you don't stick anything in, and I'll show you what this means in just a second, for difference, then it's just equal to 0. And if you don't stick anything in, basically a default argument is what happens when you don't provide that argument. Okay? And so let me show you what I mean by that. So if I do more A's than B's, and I just say length 5, right? Then what will happen is that the difference is set to 0 and the current string is set to an empty string. But if I do something like this, then the current string is actually just ABAB, difference is equal to 3, and length is equal to 5. So you can set those values, but if you don't set those values, then they have default values, and that's why it's called the default argument. Okay, so here's how I would attempt the problem. Basically what I'm going to do is I'm going to say I want more A's than B's, and then what I'm going to do is I'm going to say current string plus A, and I'm going to say current string plus B like this. Okay? But now we need to protect ourselves because this is bad, right? So think about it this way. What should length be counting, right? Length should probably be counting the number of things that are left, right? Let's use length to count down to 0, right? Recursively. Once it hits 0, we'll just print instead of recursing. Alright, so let's do that. So let's just say if not length, then we'll just print the current string. Right? Else, Actually, and then we'll just return. So this is kind of a more modern programming style that I've seen people do. Instead of using else, you can just return right here, which will punch you out of the function, and then you don't hit these two recursive calls. So now what we're going to do is we're going to say, okay, if the difference, and so what is difference going to be? I should define that for you. So difference is going to be the number of A's minus the number of B's, right? So it's going to start out at 0. And so basically what we're going to do is we're going to say, no, so the good news is, so that's a cool thing. I am returning nothing, right? This function isn't going to return anything. We are literally just exiting the function. So that's what return does for you. Yeah, so you can also, it's also a return none, right? So it's equivalent to return none. Okay, so as long as length is bigger than 0, we can always add an A to the end of our string, and if we do that, then we have used up one of our lengths, and our difference of A's and B's should increase by 1, right? Because the number of A's is increased by 1. Okay, cool. Now what? This one's a little trickier, and you have to think about it. So the length is going to get subtracted by 1. The difference is going to get subtracted by 1. And why is it subtracted by 1? Because it's the number of A's minus the number of B's. If you increase the number of B's by 1, the difference should decrease by 1. But we don't want to call this with a 0 difference or a negative difference, right? So we only want to call this if difference is bigger than 0, right? If difference is bigger than 0, then call this one. Otherwise, don't call this one. Because if you do, then what are you going to end up doing? You're going to end up putting a, well, let's see what happens if we, right? Let's comment the line out, and then let's see what actually happens if we do that. So let's call more A's than B's on 4, and let's run this thing here. So here we see what happens. We get all the different A and B combinations, right? And here we see why this doesn't work, right? It doesn't work because this one's good, but then this one's bad, because it allowed this B to happen. This one's bad because it allowed the number of A's to equal the number of B's once. The number of A's is equal to the number of B's here and here. Problem, etc., etc. So now let's see what happens if we set the difference strictly bigger than 0 and run it. Now let's look and see if this is fine. It is not fine. We need the difference to be bigger than 1 so that it will never hit 0. Is this all the possibilities? Let's think, right? Is this all the possibilities? So AAA, more A's than B's. AAB, more A's than B's. AAB, but then you know that the one thing you know is that we're not allowed to put a B here, because if you put a B here, then the thing is what? You know, it is equal to the number of B's. And that's not what we want. We want it to be strictly bigger. So that's why I'm checking if the difference is bigger than 1. If the difference is bigger than 1, then difference minus 1 will be 0, and that's the safety condition I want. So me doing this was actually wrong, because difference bigger than 0 would allow me to get a different, or I'm sorry, if difference is equal to 1, then it allows 1 minus 1, which is equal to 0, and then we add a B to that, and that creates a different 0 object, which is bad. So this one will allow only a difference, the differences to be positive. Okay, so let's int input, right? And then let's run it. And now what we have to do is we have to enter an integer. So let's enter 5. And now let's see. Let's think for a second. Is this all the possibilities, right? Well, looks right to me. AAB, AA, AAB, and you know you can't have a B here, right? Because you couldn't have it on the 4 case, so you can't have it on the 5 case either. AAB, AB. So I think this is working, unless you guys can think of a counter example. Let's do 6. All right, so we have this one clearly works. This one's fine. This one's fine. This one's fine, fine, fine. This one's good, good, right? And then this one, 2, 1, 2, 1, 2. So the difference is always 2, right? So we always have more A's than B's. Let's see what happens when we do 7, right? Let's see. You see that it kind of increases, like the number of these things goes up and up and up. So eventually you will. It's kind of, I don't know if it's exponential or factorial or combinatorial exactly. I forget exactly how these increase, but yep, that's how they increase. Exactly. It guarantees that the first 2 letters are A's, and then it guarantees that if the difference is equal to 2, then you can subtract 1. But if the difference was just equal to 1, and you subtracted 1 and added a B on, well, if you set it to 2, then that would be even weirder. So let's see what happens when you set the difference to 2, and let's try 6 now. So here are the ones for, so here's A, and then the last thing is B, right? Because it needs to have 2 of them before you can even have, or I guess actually you need to have 3 of them before you can have a B. Yep. Has to start with 3 A's, because if you have a B in the first 3 A's, then it violates this new condition here. Well, let's change it back to 1. Okay. So that's it, right? I mean, if you actually look at this function, there's not a whole lot to it, but it actually does do the more A's than B's thing, which is kind of cool. All right. I'm thinking of what I want to do next. What do I want to do next? The iterative solution? What is the iterative solution? Complicated. This is, so let me just say actually, so the examples that I'm doing today, right? The examples that I'm doing today are things where either, I'm not gonna say, and I should never say, that recursion is the only solution. There are iterative solutions. There are iterative solutions. But the recursive solution is just, you know, infinitely better, right? So, and also the iterative solution I'm thinking uses a data structure called a stack. Well, I mean, I am a little scared of it, but I'm also, the problem is that I think I could write it, but then I would have a hard time explaining it because I would have to teach stacks. So I think that I'm just not going to do that. So, okay. Yeah, unfortunately, I just don't know an iterative solution to the problem that doesn't involve simulating recursion using a stack. So, anyway. Okay. Okay, yeah, let's actually talk about classes a little bit. So, let's start on classes. So there's a keyword called class, and you can type it in. And what is a class? So a class, I think basically the way to think about a class is a new type. So basically you have ints, you know, you have floats, strings, Boolean, like I guess you would just call it bool, you have lists and dictionaries. And now you have something new. But the new thing, so I'm not going to say that a class is a type, right? Not really a type. but it's actually kind of like a type maker. Yeah, strings are also a class. So basically, class, this keyword here, is a type maker thing. And so let's just do a simple example of what I mean by that. And so you know basically what kind of, and let's just think about what kind of things types can have, right? What kind of things can types have? And the answer is, at least in Python, basically all types, even the basic data types, can have data inside of them. Sometimes we call this member variables or class variables, instance variables. Actually, I shouldn't call them class variables. I'm going to take this back. I take that back. We can call them member variables or instance variables. There's another thing called class variables, which I'll explain maybe next time. And then the other thing is that they can also have functions inside of them. Okay? And so let me make like a lion class, okay? And what are the kinds of things that lions do, right? So lions, they eat, and then they eat food, right? Some kind of food. And you notice this self. I'll talk about the self in just a second. What other things do? They roar, right? What other kinds of things do lions do? I guess they run, and we'll say run to destination, you know, right? And that's that, right? So they can eat, roar, and run. Yeah, commit regicide. Sleep. That's a good one. They can sleep for a certain amount of time, right? Okay. So that's a whole bunch of stuff that lions can do, right? And so I'll explain what this self is in a bit, but first I have to explain how to put variables into the class, how to actually stick some data in. So every class has something called a constructor. And let me explain what a constructor is. In Python, it's called the init method. So this is the constructor for the lion class. Okay? And so maybe a lion is going to have a name. And okay. So this is how you put data into the class. You always reference it by self dot say lion name equals name. Okay, so now what we've done, and let me just, before we go and kind of code up these functions or do anything else, let's just show what this means, right? So actually, I have an idea. We can say print self.lion_name has run, right? Has run to destination, right? And then we can set self.position equals destination. And something like that, right? Maybe. So say self.position equals empty string for now. And then we can print out something like self.lionname has slept for time, right? And self.lionname roars. There we go. And same thing here, right? Eats food. There we go. All right, so I lied. I did code them all up. But let me show you how. So this is making a lion type, right? But we don't actually have any quote-unquote instances of lion, meaning there's no lions out there. So let's make a new lion. What's a good name for a lion? Leo. What's another good name for a lion? It's been so long since the Lion King. Isn't Simba the lion? Or is Simba the bad guy? I forget. Hercules. Hercules is equal to lion oh god. Scar's the bad guy. Oh, Scar's the bad guy. Okay. Alright, cool. So, alright. Now we've made some lions. I swear that this... Okay. Good enough. So now we have 3 different lions, right? And so now, think about what we're going to do. So we're going to do Simba.sleep for, say, 5. We're going to do Hercules dot eat villager. And we are going to do, what else are we going to do? Leo dot roar, right? Isn't the Lion King a spin-off of Hamlet? That's not impossible. Okay. So, what's going to happen in this case? So let's watch what happens. Okay, nothing happens because there we go. You have to see the sample output for it to actually matter. So basically here, when we call it on Simba.sleep, you notice that how does Simba, right, know what its name is, right? Because we've passed in 3 different names into this lion constructor, right? We have Leo, we have Hercules, and we have Simba. How does this one know its name? Now, of course, you might say, well, it can look at its class name. No, it can't, right? The variable name is visible to us, but Python doesn't really know, right? Or I shouldn't say Python doesn't know, but like, it doesn't know. And plus, this is uppercase and this is lowercase, so it's a different thing according to Python. So how would it know? The answer is, what actually happens when you call these functions, when you call Simba.sleep5, the secret is that it actually calls sleep. It calls lion.sleep on Simba5. And that's the secret of self. So that's the secret, right? Self is actually Simba in this case, okay? When we call Simba.sleep, it does lion.sleep with Simba and 5. Here, what it's going to do is it's going to do Hercules dot eat villager, and it's going to translate that into lion dot eat, right? But it's not going to know which lion. The answer is it's going to actually feed it in Hercules and villager, like that. And same thing here. It's going to say lion dot roar, but which lion? Leo the lion. And so the point is that this self variable, it does look a lot like that. So notice how this self variable, it colors itself in purple. And the reason why it does that is because the whole point is that the secret of self, and you notice that even when you do the documentation, the secret of self is that it knows that the first argument is actually the calling class, right? And that allows you to do something like self.lion, right? Because what it's actually doing here is it's actually saying Simba.lion_name. Well, Simba.lion_name was assigned to Simba, and Hercules.lion_name was assigned to Hercules, and Leo.lion_name was assigned to Lion. So that's how, basically, I think the way to explain it is that each class has its own variables, right? Its own data. They all kind of share functions, though, right? And so you might think, well, how do they not get their data confused if they share their functions? And the answer is this. This self parameter allows you to pass in the actual class name, or I should say the class instance that you're currently running the function on, and that way you can get the right lion name, right? Because here, self is either equal to Leo, Hercules, or Simba, and whenever we do Simba.something, Hercules.something, Leo.something, then it gets passed in here as self, and that's what the point is that self knows all of its data. Yeah, something like that. You can, we might do some classes for that, so like and I'm going to probably ask you to do some of that on your homework. So for instance, yeah, each class has its own variables. Yeah. But in this case, all classes are really created evenly. There's no class, right? There's not like an upper class or a lower class. There's just class. I might make it with classes. We'll see. Project 2 might be with classes so that Project 3 can just be recursion. And we might not do classes in Project 3. But yeah, so for instance, if you wanted to make like a class battleship, anyway, so I know we've only made one type of class, but that's all we've done so far. You can imagine a lot of other applications, right? And you can imagine a lot of different ways that you can make this work. Yeah, okay. I think that's it for today. I mean, what I really want you to get out of today is that you can make this thing that's called a class, and you can declare it like it's a variable, right? Which it is. It is just a variable, so it's an instance of that class. And then once you've declared that variable inside of it, it's like a list, but it's like a more advanced list, or it's like a dictionary where you can access different things, but also it has extra functions, right? Like the dictionary object has a bunch of different functions, but you can't really add to those functions without doing any kind of like maybe inheritance or something like that. So you see the dictionary has its own functions, and it also has some variables. Here are some variables that it has. So the point is that dictionary has its own variables. It's actually a class. And yeah, so when we say object-oriented programming, 99.5% of the time what we mean are class-oriented, class-based programming. But in Java, there are other things like interfaces, and in C++ there are structs and classes, which is structs are kind of on the verge of being object-oriented, and then classes are just object-oriented. Yeah, it's exactly. We're making built-in. That's a great way to say it. We are making built-in functions for a variable type, right? It's like if you could add a new built-in function to dictionary, right? Well, Python, yeah, so Python constructors, the only difference between a Python constructor and a Java constructor is this first thing here, where you wouldn't have this this self. And then the other difference is that in most languages, your constructor is just actually going to be a function with the same name as the class. But in Python, it's underscore, right? 2 times underscore, then init, and then 2 times underscore. And so that's a little weird, but it's just something, again, this is just something you have to get used to. And I think maybe on homework 6, what we're going to do is we're just going to have you create some classes and that can do some basic things, right? Like I might have you make a ship class that can have a crew. That was one of the ideas that I came up with. And, you know, you can put a name in a list, right, or something like that. And so yeah, homework 6 is going to be about recursion, and it's going to be about classes. And so we will get to talking more about classes next week. And so good. Okay, I think that's it for now. I'll let everyone go. Hopefully you're making good progress on your projects and everybody's happy. All right, so I'll let you all go. I'll post all this code. Let's see, recursion 2. Let's commit, and so this is the end of the lecture. I'm just doing this in the lecture so that I don't forget, because I always forget. And now I will push. There we go. Once it says 3 successful, we'll head out. Push successful. Let's go.